Good morning, students. Today we will discuss Ehrenfest theorem, which is very important one, which connects classical mechanics into quantum mechanics, which links between classical mechanics and quantum mechanics. And this is based on the correspondence principle. And of course, Bohr's correspondence principle says if number of quantum particles are there, we can think of the classical particle. For more number of particles, then we can think of it's a classical particle. This is one idea. Then another idea is lambda. When lambda tends to 0, when h tends to 0, these two conditions are very important. So these three conditions are very important. One is number of particles, another one is lambda, another one is h. H means Planck constant. So if h tends to 0 or lambda tends to 0, then we can achieve classical results. So this is called the correspondence principle. And not only in quantum mechanics, but also in other disciplines also it occurs. For example, when you take special theory of relativity, when the speed of light, velocity of light is very small, it's negligible, then we can apply the same theory into classical results. So we can get the same results in classical mechanics. Similarly, when you take general theory of relativity, for the weak fields, we can get the results of general theory of relativity in Newtonian mechanics. So not only in quantum mechanics, but also several disciplines it works out. So correspondence principle is mainly based on the limit of larger quantum numbers. So we are going to have number of particles, total number of particles should be very big. And it was put forth by Paul Ehrenfest. So he was born in the year 1880 in Vienna. So nearby Vienna there was a small village. So he was born in nearby Vienna. Vienna is in Austria. Now it is a part of Czechoslovakia. He was very good at mathematics earlier, and his family they had a grocery shop, very poor family, Jewish family. They had a grocery shop. His daddy was working, Ehrenfest. His daddy was Ehrenfest. He was working in the weaving mill. And when he was 15-16 years, his mummy was no more, and daddy also. After some time, daddy also was no more. And he had 4 siblings, 4 brothers. The elder brother took care of Ehrenfest. He only taught him science and mathematics. Basically, he was so interested in mathematics. So he went to school, then he graduated in the college, and in that place we can have a degree in different universities. That is, we can study in first year in one college, then we can study in second year in another college. So first time he studied in Vienna, University of Vienna. Then he moved to Göttingen, Germany. Then he met his girlfriend. Then they got married, and she was from Russia. They got married. Then after that he completed his PhD under Boltzmann. So Boltzmann statistics, we have already learned Boltzmann statistics. So he was his PhD guide. He finished his PhD in the year 1904 in classical mechanics. So under Boltzmann. Then after that, they got married and they went to St. Petersburg, that is in Russia, and they stayed for 5 more years. Again they came out. They came to their own town, and he visited a lot of scientists in and around. He visited Albert Einstein, Max Planck, Bohr, Sommerfeld, Lorentz. So he discussed a lot of problems. In fact, he was so interested in statistical mechanics and classical mechanics as well in quantum mechanics. Phase transition. He did a lot of books on phase transition and Ehrenfest theorem. So, very good teacher in the sense his lecture will be so wonderful, fascinating. And in fact, he would derive mathematics very simple in such a way that all the audience would like his lectures very much. So on seeing the capability of lectures, Sommerfeld offered him a job. By the meantime, Lawrence quit the job. So in Vienna, so he took over after Lawrence. He took over the job. So he was a professor in University of Vienna for the longer time. In fact, he was very close to Albert Einstein too. So he invited many times to his house Albert Einstein. So Albert Einstein, after 1999, every year he used to visit his house, Vienna. So once it so happened that they had Albert Einstein and Bohr, they had difference of opinion. They did not satisfy about the quantum theory in such a way that this is probabilistic nature. And of course we know that this is probabilistic in nature. So classical physics is deterministic. This is probability amplitude, so probability is in nature. So Niels Bohr and Albert Einstein, they had difference of opinion. Ehrenfest invited both to his house and they discussed for about more than a week and they could not get the conclusion again. So he was so unhappy. So after some time, his student Kramer, most probably you would study about Kramer's rule, Kramer's in SSP. His student defended his thesis 1919. So 1920 again he invited Albert Einstein to his house and he stayed there for more than 6 weeks, more than 1.5 months. So very, very close friend of Albert Einstein. So whenever Albert Einstein goes to his house, he used to stay there and he will give some lectures. And his PhD students, as I said earlier, Kramer, then Uhlenbeck, Goldsmith. The Uhlenbeck and Goldsmith, they only discovered the concept of spin. So fourth quantum number. They were very, very famous. They became very, very famous. So Ehrenfest theorem, which says mainly about these two things. So these are all Ehrenfest theorem. And of course we know that they are all Newton's laws of motion. We know already. Okay. When this bracket is not there, expectation bracket is not there, we can say that this is Newton's second law of motion. Okay. So F equal to dp by dt, we know already. So of course these two equations are very famous equations. So Ehrenfest suggested that the dynamical variable, we can replace the dynamical variables of classical mechanics with the expectation values of quantum mechanics and we will get the same relations. So this was his prediction and he derived. So he was an Austrian physicist, as I said, and he derived this equation in the year 1927. In fact, he wanted to explain quantum mechanics. At the time, the quantum mechanics was very struggled to be explained. So he wanted to explain in terms of statistical mechanics. So he was well versed with the statistical mechanics, all because of his PhD guide Boltzmann. So he wanted to explain. By the meantime, 1926, 24, 25, 26, Heisenberg and Schrödinger, they derived equations and they easily explained the quantum concepts. Okay. So his main idea is we are going to replace the dynamical variables of classical mechanics with the expectation values. So if you write the expectation value, it will resemble the classical mechanics results. So that is the idea. The principle of correspondence between the motion of wave packet and the motion of classical particle is projected is of fundamental significance. Of course, we need to have. So as I said, when lambda tends to 0, when h tends to 0, we can achieve classical results. So this is what I said. So classical limit is lambda tends to 0. Classical limit is h tends to 0. Okay. So we can say that classical mechanics is the approximation of quantum mechanics. So we can say the expectation values of quantum mechanical operators obey the laws of classical physics. So these are all two equations which say about Ehrenfest theorems. So they are the quantum equivalent of the equations of motion of a classical particle. So as I said earlier, okay, these two things are very important. So we are going to derive these two equations. In other words, the average motion of, this is the expectation value, the average motion. The average motion of a wave packet agrees with the motion of the corresponding classical particle. Okay. So in the limit, there are three limits we discussed. One is number of particles, then another one is lambda tends to 0, then another one is h tends to 0, Planck constant tends to 0. So in the limit, when the wave packet associated with the particle reduces to a point, one expects the particle to behave like a classical one. So these particles, when they reduce to a particular point, suppose quantum particles, when they reduce to a particular point, then it has to accept uncertainty relation, correct? It has to accept. So this uncertainty relation only limits the equivalence between quantum mechanics and classical mechanics. So it's a barrier. Okay. So it provides a mathematical support to correspondence principle, and it is closely related to Liverley's theorem, which we have studied in classical mechanics, which involves Poisson brackets. So here we have the commutation relation, but in classical mechanics we have Poisson brackets. So now we are going to derive the first equation and then by the second equation. So we are going to consider one-dimensional motion of a particle of mass m, the time derivative. So this is a time derivative of the expectation value of x, which is given by this one, correct? So of course we know the expectation value of x is given by this expression, correct? So this is what we learned in expectation values, so in the earlier sessions. Okay, now you just take the time derivative on both sides. So this is time evaluation operator. So time evaluation, so time derivative, time dependent. So time dependent of x, which is given by partial d by dt. So we are talking about partial d by dt. Here it is d by dt, because psi depends both on x and t, correct? Psi depends both x and t. So we have two independent variables. So that's the reason we have partial d by dt. So now differentiate this. So when you are going to differentiate this, we'll have to keep this as constant, we'll have to differentiate this, we'll have to keep this as constant, we'll have to differentiate this. So as we know already. So we are going to differentiate this, keeping this as constant, correct? Then we are going to differentiate this, keeping this as constant. So we'll keep this equation 1.67, just have it in your mind. We are going to use this one. We are going to use Schrödinger wave equation to get Ehrenfest theorem. Okay, we are going to use Schrödinger time dependent wave equations. We are going to use. Okay, so now this is your Schrödinger time dependent wave equation, which we have studied earlier in the last sessions, correct? Now d psi by dt, of course d psi by dt is given. Okay, so we can substitute this expression 1 by I h bar. If we take the complex conjugate of this equation, we will get d psi star by dt. So that's the idea. Now you substitute here, we are going to substitute here and get the results. So that is the simple idea. Is it clear what I am saying? So just take d psi by dt from Schrödinger time dependent equation and take the complex conjugate, substitute for d psi star by dt and d psi by dt, you will get the results. So this is the idea. Okay, so now this is as I said, this is Schrödinger equation. You just bring this term 1 by I h bar this side. So you have d psi by dt, which is equal to 1 divided by I h cross the remaining term, kinetic energy plus potential energy. Okay, so multiply and divide by I. So that will give you I squared, that will be minus 1. So minus I by h cross. Is it clear? If there is any doubt, you ask me immediately. So remaining term you will just keep it as it is. Okay, you multiply these two terms. So with the minus sign. So that will give you, the first term will be exactly I, the h cross and h cross, one h cross will get cancelled. You have I h cross divided by 2m, partial d squared psi by dx squared. This will become minus I by h cross d psi. Okay, is it clear? Very simple one. And you are going to take the complex conjugate of equation 1.71. As I said, for the complex conjugate, if there is I, you just write minus I. That's all, simple one. So I becomes minus I. Your minus I already is there, so it becomes plus I. And of course, you have one potential energy term, V is here. So you will have to take the complex conjugate of V. When you are going to take the complex conjugate of any operator, this will become Hermitian conjugate. Okay, it's very, very important one. Okay, psi becomes psi star. Any operator, it will become Hermitian conjugate. Hermitian conjugate, which you have already studied in mathematical physics. You are going to change the rows and columns and take the transpose. So this is your Hermitian conjugate, correct? Just change the rows and column and take the transpose. That's all. So that will give you Hermitian conjugate. So now B equals, we are going to assume B equals B dagger, that is Hermitian conjugate. Okay, it means we will get the real eigenvalues. So we studied already that if it is a Hermitian conjugate, the answer will get the real eigenvalues. Okay, so that's the reason that V becomes V dagger itself. Okay, so now we have taken the complex conjugate of this. Okay, now we know d psi by dt, we know d psi star by dt, so we can substitute in that equation 1.67. So we will substitute 1.72 equation and 1.71 in 1.67. See, this is the equation. D psi star by dt is given by this term, d psi by dt is given by this term. Okay, your xy is here and x psi star is here. Okay, x psi is here, you have x psi star is here. Is it clear? Equation 1.73, very simple. Now you multiply this term inside, you bring it to this term inside. So it will give you minus I h cross 2m, you have x psi, so x psi d square psi star by dx square plus this term multiplied by this term. Again you multiply this term with this term, you will get this term and you will have this term. Okay, come on, is it okay? 1.74, you multiply xy inside, that's all. So you have 4 terms now. And of course you look at this term, second term and fourth term. As I said earlier, V equals V dagger. Okay, so both the terms will get cancelled. Okay, so now we have only 2 terms. So remaining 2 terms I have written in equation 1.75. Okay, so this term is here and this term is here, and I have written this term on this side and this term here this side for the time being. Okay, just I have changed, I have written, and I have taken I h cross by 2m out. Okay, I h cross by 2m out, I have written this term here, then minus this term. Very simple one, 1.76. Is it okay? Up to 1.76. Now we are going to integrate the second term alone. We are going to, I have written the same equations here. I am going to integrate using integration by part. Okay, we are going to integrate both the terms. We will take, for the timing we will take the second term and we are going to integrate using integration by parts. Okay, this equation we are going to have the integration by parts. So this equation, same thing equation. So you look at this equation, I have changed this one, d squared xy psi star, because this is Hermitian, we can change, doesn't matter. Okay, look at this term, I have brought xy here, psi star here, see, psi star xy, both are the same. Okay, both are the same. Is it okay? Now we will term this is udv method, and we know already udv equals uv minus v du. So we will keep this term as u, this term as dv. Okay, so dv is here, dv becomes d squared partial d squared xi by dx squared. So integrating that will give you v, which is nothing but you have to integrate on both sides, that will get v. So v equals dxi by dx. Is it clear? Just integrate on both sides, you will get this one. Now v equals, this is x and y both are variables, so you have to differentiate with respect to x first time, then keeping x as constant, then psi. Okay, so keep x as constant, you just differentiate this, that will give you d psi by dx. Keep y as constant, you differentiate with respect to x, so that will give you dx by dx, that will give you 1. So your v is obtained, so v is known. Okay, so v is known, u is already, it is there, only thing is du just to differentiate, you will get du, d psi star. So you have this one, this term, which is equal to uv minus v du. Is it okay? uv minus integration v du. Okay, this term, look at this term, we have given the limits minus into plus infinity. We have already studied in the session of interpretation wave function. Okay, there are five very important points. The last one is psi should vanish at the boundaries. Can you remember? Psi should vanish at the boundaries. At infinity, psi should not be there. So at infinity, psi should not be there. Psi will become 0. Psi will become 0 at infinity. So this term will become 0. So this term alone exists. Is it okay? So this term is contribution from integration of v du. So this is v, this is v, this is du. Okay, for the earlier. Now again you just integrate integration by parts. You are going to integrate this one, integration by parts. This term alone. You will get the answer. So for these two problems, these two theorems, you will have to integrate 2 times. You will get the answer. Okay. So now you just keep this as dv, this as u. Okay. This is u, this is dv. Okay. Earlier we kept this as u, this as dv. All because of this. Okay, that is the idea. So now this one is there. So you just keep this one as dv. So v becomes immediately psi star. Simple one. Okay. So now you are going to keep this as u as this term. So u equal to x d psi by dx plus psi. Now we need to have du, correct? Use the same formula. So du equals, you just differentiate, that will give you x d squared by dx squared plus you will have to differentiate x. So answer will be 1. So d psi by dx. Is it clear? Plus you will have to differentiate d psi by dx. Come on, is it clear or not? If there is a doubt, you just ask me. We are going to differentiate this. Keep this as constant, differentiate this. Keep this as constant, differentiate this. Answer is 1. Okay, that is dx by dx. Answer is 1. Again you differentiate, you will get this. So the final answer will be, this one will be, du will be, here x is missing. So x d square psi by dx square plus 2 times d psi by dx. Okay, here x is missing. See? Now use the same formula, u dv. Okay, u dv, 1 minus is there. 1 minus already, 1 minus is there. So this will become minus. Then minus is there. So minus minus plus, so plus. Is it okay? This minus. We have only integrated this term. Okay, 1 minus, then plus. Then this term is psi star, that is v du. This is your v, this is your du. Is it clear? Now again use the same thing, minus into plus infinity. This term will go off, will become 0, will go off. Okay, so you have this term alone. Is it clear? This term alone. So we'll have to substitute in this term. We'll have to replace in this term. Correct? We started only from this equation. Can you remember this equation? So you have x psi star d squared psi by dx squared. That minus sign is there. So minus sign psi star x d squared by dx squared plus 2 d psi by dx. Is it clear? This equation 1.77. Any doubt in this equation? Any doubt? Okay. So now almost we have reached. So this term, you just multiply psi star here. We will get these 2 terms. We can cancel first 2 terms out. Okay. The last term alone exists. See here, we are going to multiply psi star x, and these 2 terms will get cancelled. So I have done the same. The last term alone exists with a negative sign, with a minus sign. And this IH cross with a minus sign, I have brought it inside. Okay. The reason is, I'll tell you, IH cross with a minus sign, so minus IH cross. These 2 and these 2 will get cancelled. You have 1 by m psi star minus IH cross d by dx. Minus IH cross d by dx is p. P equals minus IH cross del. So we can replace this term with p. Okay, so the expectation value of dx by dt, okay, time derivative of expectation value of x, that will be 1 by m of this term. This term is nothing but the expectation value of component of the momentum. Can you remember? The expectation value of the component of the momentum. So 1 by m multiplied by p of px. So your px will be m dx by dt. Okay. Generally we can say that p equals m into dr by dt. So that was the equation, first equation we wrote earlier. Okay, this is the equation of motion. Suppose if we remove the expression value, so it will become P equals m dx by dt. P equals mv. V equals dx by dt. So P equal to mv. That's a classical result. Okay, the expression value will be in quantum mechanical region. In the limit number of particles are there, then this will results will be exactly matches with the classical mechanics. That's the point here. Okay, so this is the classical equivalent relation. This is one equation. We have solved one equation. Okay, so now we'll go for the second one. So any doubt? Solving one equation, we have solved one equation. Okay, any doubt is here?